So, thank you for coming. This is the third session of PPDP, okay? And it is an honor to, well, you didn't write that, but so if you see the program, okay, this is a talk for the 10-year award, okay? So this is really a paper published 10 years ago that the steering committee of PPDP, okay, decided to give this award, okay? There is no money, sorry. Okay. There is no...
that's the first thing my children ask.
There is no piece of paper. I can prepare one for you and send it to you, okay? But you see, but in the program it appears really as a 10 year, okay? So we have 1 hour and a half, okay? But you see, it's as much as you want, okay? Because there's a coffee break after that, okay? So thank you very much. Okay, you're going to start.
Thank you very much. Yes, so I guess 3 months ago, I got an email from Santiago and others to say that this paper had won the 10-year Most Influential Award for PPDP. I thought, oh, this is really nice, thank you very much. It's a very nice thing to happen. The only thing is that, well, we've all moved on. I'm not working in this field at all anymore, and nor have my co-authors. So, now I've got to present work that was 10 years old and update it as well, because I have no idea what has happened in the area since. But I'll try and do that. So I'm no longer at Microsoft, I'm at Meta, along with Nick Benton, one of the co-authors, and Jonas Jensen, who he had some of his PhD was based on his work. He's now working at GitHub, and Pierre-Evariste is in Paris.
Sorry, it's better if you get...
Yes. So I'm going to try and give you a flavour of what we did in this paper 10 years ago, and a little bit about another paper we wrote, which was published at Popple, about the logic associated with the work. And then at the end, I'll say bring us up to date a little bit, in as much as I can understand the field still. So here's the outline. Yeah, so firstly I'm going to rewind, talk about what was our vision for why we did this work, and then a kind of recap. Sorry if people were here 10 years ago, but some of the slides are the same from then, and a little bit of a kind of commentary on, has this stood the test of time? And then, so fast forward, I've had a look at some of the people who cited our work and related. So a couple of highlights, I feel, from recent work on machine code, spec and vec. And I'm going to indulge myself with a little bit of work that I did at Meta with Nick, which I feel is kind of related. I'd say it was a bit inspired by some of this work. Okay, so and do dive in with questions at any point, please. So this was our vision. I can't say that we've realised this vision, but this was it. That we want to build proofs of safety for an operating system running verified code, where you have a kind of end-to-end property that says these processes are isolated simply because through proving correct rather than through some kind of memory protection mechanism. So here's a kind of picture where you have, so it's the idea we have like applications running over the top of some operating system, and everything is verified from the ground up. With kind of proof of the high-level code, and some kind of typed assembly language was the idea we might get to eventually, and checked by Coq in this case. And I think what's maybe still a bit unusual about this work is that we built everything inside the Coq proof assistant. So there's no other languages involved. We model the machine code in Coq, bits, bytes, memory, all that kind of thing, including like instruction decoding and execution. We even generate machine code from Coq. So we have and that's why we say it's the world's most powerful macro assembler. You can write assembly syntax basically inside Coq, and then use Coq to actually produce the machine code, and even then run XEs and DLLs, and it was on Windows, of course, because I was at Microsoft. And then we can specify and prove programs correct inside Coq. And obviously, that's the more traditional use for Coq. We built like a separation logic for low-level code. That was the subject of the Popple paper, and various tactics showing that programs meet their specifications. So there's a ton of other work in this space, but I don't think anyone else tried to do everything inside, one place, which was the Coq theorem prover. So why PPDP, you might be asking? Well, if you think of languages as sort of inhabiting a continuum, then there's one end is imperative and machine code, and assembly language definitely falls into that. And at the other end, declarative, well, you could argue Coq is pretty as declarative as you can get, really. It's, terminating, based on type theory, very high level. So our goal was to use this highly declarative language to, like I just said, model and generate, and specify and prove programs that are written in a highly imperative language. That's x86 assembler. So why Coq? I mean, it's got a very rich and higher order and dependently typed type system, and that's obvious for a lot of things that you want to model in machine architectures where you want to parameterize over things like bit length. Dependent types makes a lot of sense. It also has a lot of conveniences, which doesn't really relate to its use as a proof assistant, but it means we can actually write assembler syntax actually in Coq itself. And you can write programs inside Coq in a functional style and run them. So that's how we actually generate code from the proof assistant. But of course, I mean, as is often said, it's got a very steep learning curve, but it's addictive, as it's been pointed out. So it was a lot of fun. So here's, don't know, just kind of curious actually, because who here has ever programmed in assembler or machine code? Okay, so probably more than half. Okay, so this is the assembler syntax for x86, 32-bit x86. What does this program do? I think it's, maybe this is the factorial function. So it's the Intel instruction syntax. There are other variants. There are labels here, so you don't have to write actual addresses in your jumps. There's various other things which don't relate necessarily to instructions, like inline string data and so on. And there are macros. So here there's a macro for a loop, and there's a macro for calling external code. Now you're probably going to predict what I'm about to tell you, which is that this is actually just a definition in Coq, even though the syntax looks like what you would feed into the Microsoft assembler. So the assembler syntax itself for the instructions is just user-defined Coq notation. So Coq has this nice notation facility, basically kind of extending the grammar of the language. And the labels, we're using a kind of high-order abstract syntax to trick to get labels into the assembler code. And macros obviously are just definitions in Coq. So the while macro is just a definition of function in Coq. Yes?
When you say user-defined notation and it's assembler code, do I as a user have to specify the full x86 assembler code first before I can call it?
We did that.
Yeah, so it has to be added.
It does have to be added. Yes. So yeah, I'll come back to that actually later. So that is a bit of a disadvantage, I suppose, of this approach. So not only can we write this and model it and prove it and so on, but we can also use this to generate code. We've got an assembler that is implemented in Coq. So here we've used that assembler to build an executable. So we've even got the format for linkable executables with some standard syntax. and then we say generate the bytes at a given address to load this. And then compute is Coq's kind of declaration to say actually run this code. And there, we had to do a tiny little thing which we couldn't do in Coq, I think, which was to convert the hexadecimal into a binary. But that's the only thing outside of Coq that we're using in order to generate this binary, and we run it. There it is, factorial running. I'm not going to try and do a live demo. I've not even tried to get the source code from 10 years ago of running on this machine. But or we can even, and this was quite fun, run it on the raw metal without even an operating system. So you can link it with the sort of standard bootloader, and at the time I did this, you would probably have plugged a CD into your laptop. So this was, I wrote Game of Life in machine code using Coq and then running on the bare metal, which is a lot of fun. So obviously what you want to do is then prove something about this. We didn't get that far for Game of Life at least, but in principle we could have done proofs. Okay, so I'm going to now do a kind of recap of the three things: modeling of x86, generating code, and specifying and proving. So start with nice use of dependent types for vectors of length n, basically, for all the different kind of n-bit words that you want, with various notation, some functions. So to compute the, what's this doing? I don't know. It's stripping off n bits off the low bits off a bit vector. The point here is that not only are these things we can prove theorems about, but you can actually execute these things, and that's how we actually built, the assembler and so on. And then write functions to do actual machine arithmetic on these vectors. So this is what's this? This is compute doing the adding 2 bits with carry and all of that kind of thing. So it's very algorithmic, so we can compute. But then to actually prove things about, like machine arithmetic, it's a bit painful to prove in terms of the bit representation. So, and we've got all these libraries in Coq, like SSReflect is this library of mathematical proofs. So we exploit the fact that the integers modulo 2 to the n there's an isomorphism between them and our bit vectors to actually compute in one place but reason in the other. So you can see an example of that here, which is showing that addition is associative. And this is a little proof script from Coq that does that, exploiting the isomorphism, and then using some existing lemmas from SSReflect, the maths library, that give you associativity, say, for addition. Okay, so now I'm going to talk a little bit about how we then model the x86 ISA, the instruction set architecture itself. Machine state is pretty straightforward. There's some registers, there's some flags, and there's memory. We only modeled sequential computation, so didn't have to get involved in weak memory models and all that kind of thing. But other people have studied that. And this is just a subset of x86, but enough to demonstrate things like factorial, Game of Life, and so on. So the x86 is kind of notoriously complicated. There's a lot of, especially the instruction formats, but I'd say Coq was pretty good at abstracting enough that you don't have to kind of just enumerate all variants of instructions in some big data type or something. You can parameterize on various things like addressing modes and so on. So then we need to model instruction decoding, because unlike some other work where you start at the assembler level and you're modeling that like you would model a programming language with a sort of abstract syntax tree, we want to start with the binaries. We want to actually be able to give an interpretation to machine code on the metal. So we have to model instruction decoding, and we did this via sort of a little monadic, some shorthands. So you can see it's literally we're sort of switching on the byte that it's just read from the memory and then reading some more depending on what instruction it is, and then producing the sort of abstract syntax tree of the instruction. And then instruction execution was just like a partial function from states to states, also using a kind of monadic style. And putting it together, we just have this state-to-state sort of transition function that, what's it doing? So it's probably worth just stepping through this. So it's saying pick up the instruction pointer from the register state, that's old IP, do the instruction decoding, which gives you back an instruction and the new instruction pointer, set the register with the new instruction pointer, and then actually evaluate the instruction. Okay, any questions on that? No. Okay, so now I'm going to talk about the other side of things, which is generating x86, not reading x86. So what you saw there was using some kind of data type in Coq to represent the instructions, but it's a bit painful to construct unless you're doing, you're building a compiler or something. If you actually want to hand write this stuff, then it's nice to have something a little more high level. So we mimic like you saw, Intel instruction syntax using the Coq notation feature. So this, Microsoft or Intel standard for writing x86 assembler translates just using the notation feature into this construction of some data type value. And then you want to be able to build programs which are sequences of instructions, but they also involve like labels, abstract labels, and we had a kind of high order abstract syntax like trick to write those so that you, I think, it's a lambda, is it? Yeah, there we are. The body of this thing which gives a label is actually a function. And so now we have to implement instruction encoding, and I'll come back to this because obviously we want these to agree, and it's a bit painful to write this twice. If you look at the 2,000-page Intel ISA, then they'll have these diagrams of instruction formats. They won't talk about how you actually implement encoding, and obviously the chip implements the decoding. But we had to do both sides. So this is again like a monadic style. It's just sort of switching on this abstract instruction and then literally writing out using the monad the instruction format. And then using this encoder, essentially we're implementing an assembler that determines some assignment for the labels that works. And then obviously we want to prove some kind of round-trip theorem that says that the instruction decoding is an inverse with respect to encoding. So now we've got a way of writing instructions. We can build little abstractions just using Coq definitions. So this is, what is this? This generates some code that computes the maximum of 2 registers. And you can see it's using the label syntax to do the sort of jump over the move instruction. And here's another one that does a kind of if then else. And the macros can obviously be parameterized by anything you like. So could be by values or registers or whatever. Yeah, so they can use any Coq feature. So here's a macro that's recursive that actually generates a sequence of shift and add instructions to compute, to do multiplication, basically. And I'm using, what's this, natural numbers in Coq as the number of bits. So we took this further, and there's much. I'm not going to talk in detail here, but one of the co-authors, Pierre-Evariste Dagand, did this work on regular expressions. So you can go all the way up to some high-level DSL, a very declarative thing, and use Coq to sort of make the connection between the high-level DSL and the underlying implementation. So what he did was compiled a regular expression to a DFA. Using this was quite nice because it was just using an off-the-shelf, if you like, existing Coq library and proof of correctness, and then he did the translation from this DFA down to assembler, and so you've got the whole kind of chain. Okay, so now I'm going to move to the way we use Coq to build a logic to specify and prove correctness of machine code. So this is mostly covered in another paper, which was the same year. So the first question that kind of arises is, why do we need a special logic for machine code? So it's common, when reasoning about high-level programs to use something like Hoare logic, where you've got a command and then a precondition and a postcondition, the sort of well-known Hoare triples. And in the last 20 years, we've got separation logic that makes reasoning about pointers tractable. So can we just take this and use that for machine code? Well, some people have done that, but it suffers from a couple of things. Well, firstly, machine code programs don't really finish. They just keep running. So there is no postcondition. And also, code and data are all mixed up. It's not structured. There isn't sort of structured control flow like you would use Hoare logic for. And code can be kind of higher order, where you've got code pointers. And so what we did instead was, instead of a Hoare triple, I've seen it referred to as a Hoare double, where you kind of have there's a precondition, but there's no postcondition. You're just saying this code is safe to run under this precondition, and that's roughly what we did. And you can recover Hoare triples for actual structured code by a sort of derivation, a kind of CPS-like thing. So, yeah, we built an assertion logic, which is like a predicate on states. This is like a lot of work that was being done at the time on separation logic. And we had to build in various technology that was also around at the time, step indexing, to get, these, I don't fully understand all of this stuff actually, but later, and frame connectives. But then the safety specification is in a kind of continuation parsing style, and you'll see that in a second. So here is actually a Hoare triple defined in terms of our safety predicate. So basically this is saying if it's safe to execute code where the state begins with the instruction pointer having J in it and some precondition Q, then it's safe to execute code that precedes that. So that's why it's a sort of CPS-like thing. So this is the precondition, P, and this is the postcondition, Q, and the instruction pointer starts at I and ends up at J, and this is then saying the code is actually here between these two pointers. So we've defined, just in terms of this kind of Hoare double, we've got a standard Hoare triple just as a derived thing. And then you can derive rules that in separation logic you'd be familiar with, like the frame rule, just as a consequence. So here's an example of how we would use this to give to specify what it means for a particular instruction. So this is the push instruction. So push a register onto the stack, and you can see we've got a kind of precondition where the stack pointer starts at SP, and this is what was at the top of the stack before running the instruction, and then afterwards the stack pointer has been decremented by 4 and it now points to the value that we've pushed from the register. So you can and then you'd prove this lemma basically using our semantics. But the idea of lemmas expressed this way extends not just to instructions but to, say, macros. So here's the macro we had earlier, which was the sort of multiply by doing multiple shifts, and this is a lemma that says how that behaves in terms of precondition and postcondition. So here's an example of proving a very, very small program. So this is swapping 2 registers using exclusive OR, the exclusive OR trick, for swapping registers without using a temporary. So 3 exclusive ORs, and this is the spec, basically saying that there's a precondition where registers are this way around, V and W, and then postcondition, they've been swapped, W and V. And we have to say something about the flags because we're going to mess up the flags by doing these instructions. So, and I'm not going to go through this script, but this is the Coq proof script for showing that spec is met. So we have a little bit of automation, so some tactics in Coq, but you do have to do quite a lot of manual proof. Probably down the bottom here we're even using, well, some of these would be lemmas that we'd probably proved using this mathematical library SSReflect. Okay, so that's a quick overview of what we did with the logic. So now I'm going to sort of look back a little and say, well, what were the limitations and what has happened in the last 10 years? Now, I don't know what's happened in the last 10 years. I just had to look at the people who've cited us and ask around a little bit. So I'm just going to select like 2 or 3 things that I think are kind of interesting that have happened in the last 10 years. So obviously the limitations, there's some obvious limitations. One is that it's a rather small subset of just 32-bit x86. So it's not comprehensive. And the other is that we had to construct this thing very much by hand. We might have got it wrong. So how can we trust this thing? It's not authoritative. I think we did consider, how we might test the spec that we got against actual execution, but we didn't get that far. You just have to trust it. So one thing that's actually happened in the last 10 years is domain-specific languages for specifying the semantics of processes. That's the ISA. So when we did our work, I think this was just starting. There was a language called LEM, but if you look in most processor references, so if you take the Intel one, it's 2,000 pages. It's all in English. I mean, there's kind of no formalism there. Other specs are better. So ARM, they have a kind of a way of describing things that looks almost machine readable. And actually people have done that. They've taken the ARM spec and scraped it and turned it into something that is machine executable because it's written in such a kind of pro forma sort of way. But one thing that's happened is these languages have been devised, and the most prominent, I guess, is this language called Sail, which is mostly the University of Cambridge, where you can specify the ISA. And there's now Sail specs for various subsets of various processors. And in the case of ARM, they even generate the sales spec directly from the internal definitions. And even better, for RISC-V, it's actually been adopted as the way they are going to, specify the processor. So that means we could use that rather than having to handcraft stuff. And that's what's happened with, so for example, this is a recent paper from last year at PLDI by some of these folk involved in SAIL, where they've kind of connected all the dots. They've got a model of machine code and a logic, and it's kind of what they call authoritative, means you can kind of trust it because the spec is the real thing. So this is their kind of, you probably can't see all the boxes here, but this is their high-level diagram. So it is comprehensive in that it's, say, a large subset of x86, and authoritative, you can kind of trust it. And they use some of the similar tech that we used, so separation logic or doubles and so on, similar in spirit. But I think, in my mind, there's still something missing. One is that there's a lot of languages being used here. So there's this language called SAIL. They've got another language called ILA, which is used to describe, it's like a microcode, I suppose, so you can express high-level instructions in smaller units. And that all sort of sits outside what you would call the trusted computing base. So all the stuff outside the box that's got cock inside, you just have to trust. And it's also not clear to me, and I haven't spoken to the folk involved, whether all of this stuff can be kind of abstracted in the way that we've done. So you could build an entire verified compiler, say, or that regular expression DSL, all inside the same system, because they're using SMT solvers and various translations. So it's not clear how much of this stuff can be abstracted, but it's pretty impressive. This is quite good. So the other thing that I'd sort of like to comment on is the encoder and the decoder, which we had to write in this kind of monadic way. It's not really very declarative. At least we proved they're round-tripped, but it was pain. The instruction format itself is kind of buried in the encoder and decoder functions, whereas if you look at an actual spec from a processor manufacturer, then they'll describe the layout of an instruction. So here's a paper that I've found does something quite nice, which is what they call bidirectional grammars basically for this problem, machine code decoding and encoding. So the idea is you specify the instruction format in a declarative way with a little bit of dependent types, because there's lots of dependency in instructions. And then you can derive the decoder in the encoder and the theorem kind of by construction. And it kind of fits into the same sort of flavor as we've got, which is everything's done inside cock. And they've applied it to x86 and MIPS instructions. So if I was to do this work again, I think I might use something like this. Okay, so the last thing I want to talk about is something that I've done since I've been at Meta, because I've not done any of this machine code verification stuff. But I'd say perhaps the way we did the whole logic kind of inspired this a little. So I've been working on this language called Hack, which is the most used language at Facebook. It's not used anywhere else, really. And it's derived from PHP. So PHP is a disaster zone of a language, but unfortunately, Meta had a million lines of code in it. It's what powers Facebook, basically. And they needed to do something about the various disasters. And so they kind of evolved it into this language that looks more like C# or Java or a sensible language. So that's what I've been doing, working on its type system. It has an unusual feature, which is not the worst of the features, really, which is that locals aren't declared. They don't have lexical scope. I don't think that's as bad as it sounds, but it would be nice to infer types for them, make them safe, and to do that, you need to do this in a kind of flow-sensitive way. So I'll show you some examples in a second. So we need some quite rich types to do this. So we use union types at join points in the program, and we also use intersection types when we refine the types of locals by testing them for like runtime tags. So here's an example of using a join point. So here, this is a function in hack. It takes in a Boolean and it returns mixed, which is just top in hack. And then it branches based on this Boolean. Does some, I don't know what it's doing. It's doing some assignment to this variable x. But you'll see that when it leaves the condition, the variable is either an integer or a string. So, and then when we return it, then, well, you can return anything, but the point is that internally, hack will actually give this variable, this union type, into a string. Now, that's straightforward enough. But what about more complicated control flow? So hack has the usual stuff you would get from C-style languages, but with exceptions. So we've got catch, we've got finally, we've got break, we've got continue, and you can have something really quite complicated where variables get assigned different types, and what type they actually have depends on the control flow. So in fact, there's an error in this program. It might not return a string. Let me see. Anybody see where that might be? Ah, yes. If you enter the loop and I is smaller than 5.
The break, will need an assignment, right?
Yeah. So when you break, it'll break out the loop, and S will have a Boolean in it. Yep. So, and when in 2016 at least, hack was kind of broken. It managed to do join points, but some of this stuff just was not sound. So how do you solve this problem? So this was what we did. The idea is that at any program point, there's kind of a fixed number of possible continuations. There's the next statement, the usual continuation, but there's also the break continuation, so to the end outside the loop, the continue continuation, and then catch and finally for exception handlers. So just to show how we handle that, I'm going to take a very tiny subset, just 4 or 5 slides, to show you how we do this. So here's a little subset of hack. It's got expressions, it's got statements, the usual kind of looping constructs, but breaking and continue as well. And it's got subtyping. And for typing of expressions, do the usual thing, define a context for the locals, and then define a typing judgment for expressions. Fortunately, expressions can't now at least make assignments, but they used to be able to, so we had to deal with that at one point, but we killed that off. Now to type statements, and this is where we use continuations, we define another context which contains the possible continuations, and the continuations are typed with how the locals would be typed when you jump to that continuation. So, and if anyone is familiar with the work from years ago of typed assembly language, they had a similar idea there. So here we've got the next continuation means it's safe to move to the next continuation with an integer in variable x, but it's safe to break with variable with x containing a string and so on. So the judgment for statements then includes these 2 contexts, and you'll see the similarity with what we did with the x86 logic, which is it's safe to execute this continuation under this bunch of locals, or in x86 any state satisfying some precondition. And then we can implement that as an inference algorithm for inferring the types, because you don't have to put types on locals in hack. In fact, you're not allowed to. And it's essentially computing like the weakest context such that this will hold. Okay, so coming to my conclusion slides. So there have been a lot of advances, most of which I don't know about, since 2013. But one thing I still haven't seen actually is using the sort of cock for everything, where you're doing it all inside one environment. I mean, we used to talk about this being the sort of ultimate IDE, where you write your code, you specify, you model it, prove all in one place. And it kind of encourages this modular use of little languages and just building DSLs and very fine-grained abstractions. Okay, so my last slide is a sort of personal one. So I was sort of thinking, I started out my computing career, if you like, when I was a boy, many decades ago, programming in machine code. So cue embarrassing picture of me from a very long time ago. So my first experience was Z80 machine code, assembled by hand into hexadecimal. And here I am, doing this in a theorem prover in Coq now. Okay, thanks for listening.
Questions?
So I have one great talk first.
No, it's on.
Oh, okay.
For recording purposes.
Okay. So I have one question about your use of notation, right? This approach seems to rely heavily on Coq notation. What is your experience with that, and how difficult was it to hack that syntax into the notation mechanism?
It's a horrible hack. Yeah, it's only just possible, and I think it was a kind of trick. But I can imagine it would be nice to have a better thought out way of just switching into your own, a new grammar, and providing a full, parser or something, rather than just using these notation tricks.
So last year Splash, I made a workshop called Unsound, Sources of Unsoundness in Verification, where basically one of the kind of conclusion, okay, not mathematically proved, but informal conclusion is that when you extend whole logic with either dynamic dispatch or first-class functions, it's very, very tricky to not make it into an unsound system. And you have mentioned that your Hoare couples, one of the things that you were trying to solve was a dynamic code pointer, basically.
Yeah.
So can you expand on how you did it soundly?
I think I'd have to refer to my co-authors for details there, but look in the Popple paper, because it does talk about higher order specifications, and in fact the other people doing similar work, like the Islaris work, I mean they do higher order stuff as well. So for example, they do kernel level stuff like installing exceptions in exception tables and all that kind of thing. Yeah, I don't know whether I've got an example here of that, but yeah, it is tricky, but yeah, I think to refer to the paper.
More questions? I have a couple of questions myself. Thank you very much for the presentation. Okay, I think that was very inspiring. Okay, and so I have a couple of questions, comments, just to think. So one of them is this kind of gap, right, between the formalisms and the actual implementations, or the more industrial things. Okay, something like that. Okay, so that there is really a gap, and at our level sometimes it's difficult to make it clear whether there is still a gap or not between representation, things like that. So that's like one question, okay? And the other one is that, would you consider your paper like ahead of time, or or do you think that at that time it was already like you see, like a movement towards these kind of things?
So the gap, I think, I mean, the paper that was at Popple was, the title was it high-level types for low-level code, I think, something like that. And I think that's the point, that you've got these, you can have quite expressive types that describe very low-level code. So it's the abstraction that gives you that. So, and you could see that with the regular expression example. We used some off-the-shelf, high-level thing in Coq that compiled regular expressions into DFAs with a proof of correctness, and then we took the next step of then doing the translation into assembler, and the whole thing is proved from top to bottom, and the theorem that connects them is quite abstract, and you don't need to worry about the machine code. What I don't know is what we never got to work out is how to scale this. I mean, there were tiny programs. To do this for an operating system, you absolutely need a bunch of automation. And my feeling is that then you would lose the ability to abstract. Well, because you'd be proving.
This Australian company, right?
Oh yeah, yes, SSR, yeah. But I don't know. There have been advances, and so the next question was, was it ahead of its time? No, there was a bunch of other stuff going on at the same time. So people like Magnus, Myrene, and others were building models of processes and building separation logics. I think the Popple paper did this. I mean, the thing that I can't explain because it's not I'm not the expert, but the higher order code pointers, that was novel. At the time, that was ahead of its time.
You have more expressive power in some sense using Coq or many of these formalisms, okay, to express capabilities or features of these underlying languages.
Yeah, well, I mean, I think the Popple paper was almost independent of Coq. It was the logic itself that was an advance. But there were a lot of people using Coq in a similar way. I mean, I'd call out what's his name, Adam Tripala, and his Bedrock work. He was kind of using all the abstraction facilities of Coq to do advanced programming. Yeah.
Okay, thank you. Any more?
This is perhaps my fairly limited awareness of what's been happening in this space, but from my understanding, I think a lot of work in the past 10 plus years sort of focused on doing, I'm thinking of this kind of verification of very low level aspects. Yeah. So like Peter Sewell's group, right, they worked a lot on Isabelle, right, rather than Coq. And I was wondering if you could comment on perhaps why they chose Isabelle rather than Coq. Is perhaps Isabelle better suited somehow for a bit tongue-in-cheek, but
they tend to. Isabelle has more automation, I think, but it doesn't.
Libraries.
Yeah, but it doesn't. I mean, I think it's habit as much as anything. There's only one theorem prover you can hold in your head at one time, really. But Coq is more expressive as a language because it's got dependent types, and that makes it very suitable for these very parameterized definitions. So some of them, yeah, I mean, if you look at some of the work on modeling of machine code, there'll be more lines of code because they have to describe every variant of the instruction separately rather than being able to abstract out the commonality in a way that ends up becoming dependent. Yeah.
So you mentioned the problem of being the authoritative spec, and some of the follow-up work which was that, but then there was this blow-up in terms of what is outside the trusted computing base, right? So do you have any answer, like vision of how to reconcile these like conflicting, constraints in a way.
You mean the fact that even though the spec is authoritative, you're then using some untrusted
you have
tooling
to have a complicated tool chain. Whereas in your example, everything was in Coq, but then you relied on. You already said you put it to the limit, the notation and stuff. So maybe that doesn't scale to a real thing either. So what would be the right approach there if you want to do it?
I think that's still being explored. I mean, the Islaris paper does talk about the limitations, and it does talk about this issue of having to trust their translation, trust this SMT solver. I mean, they do a little bit of translation validation rather than verification, I think. But then I kind of think if they're doing translation validation, this is my question really of them, I should go to them, I guess, is how do you abstract that? Because they're validating a particular translation of a particular piece of machine code, not the output of a compiler or something. I mean, whereas ours, in theory, could connect to a verified compiler. But yeah, I don't know what you do about them. So I mean, they have this interesting observation, which is that if you try and model the whole of something like x86, then even giving the semantics to a simple instruction is like hundreds of lines, because it all depends on various configuration flags and stuff. Is it running in kernel mode? Is it running in user mode, etc., etc.? And there's address translations and all sorts of stuff going on that we don't have to worry about because we've abstracted away from that. But if you want to do the whole thing, and what they do is they have something where they kind of that Euler piece of the diagram, it specializes the instruction for the particular kind of configuration that you're running it in. So you don't see these hundreds of lines. It boils down to something much smaller. But again, you've got to trust that. I don't know.
To expand on this discussion a moment, in general, all of this work on verification tend to be about chains of trust. Like, for example, if Coq is actually unsound and you can prove false, of course, none of your work. But proving false in Coq is so valuable on its own that once you have verified something from a set of assumptions, what you have really done is to say, either I have done it correctly, or another of those big important things was broken, and finding that out is also exceptionally valuable. So that's where you can put layers of abstraction somewhere where, for example, to put it at a completely different level, you can say, oh, look, I have a JVM or a VM in general. I can assume that this has a specification, and I can prove the correctness of my code, assuming that my virtual machine followed the specification. And again, if the VM is broken, sure, your code is broken, but if your code being broken proved the brokenness of the VM is still very valuable. That's how you build value in those verification settings. Anyone else?
Yeah, so we still have time until the coffee break, okay, because it's at 3:30, okay. Thank you.
Thank you
okay, for your
inviting
talk.
me.